Well, hello guys. So today I just remembered we forgot to talk about the antenna problem. So let's just briefly recall what the problem was about and see if you are able to solve it. So you have n components or n antennas, m of which are defective and n minus m are functional. Defectives cannot be distinguished among themselves, and functionals cannot be distinguished among themselves. How many linear orderings are there in which no two defectives are consecutive? You understand? So you can imagine batteries. Some batteries are working, some are not. You cannot tell. Let's say somehow you can see which battery was burned out, but you cannot say you cannot distinguish burned batteries among themselves or functional batteries among themselves. How many linear orderings can there be where the defectives are separated? You understand the question, guys? The defectives are not together. So did you think of this question? You have? Do you have an answer? If so, type it in my notes. Type it, I'm sorry, in my chat.
Hi, Arkady. Can you pull up the board so I could see the problem?
It is shared. It is here. You can see it?
Not the top part.
Like this?
Yes, please. Thank you.
Good?
Yes. Can you hear me?
Yeah, I hear you.
Okay.
And guys, a lot of you are invisible. It would be nice to see your confused, sweet young faces. So turn the cameras on. Let me enjoy. Good, good. All right. So this problem, I mean, if you haven't solved it before, then you haven't solved it. You either know it now or not. So let's go through the solution, guys. The situation here is, as with many combinatorial problems, is to fixate on that aspect that you should count best. I see that you need to create a protocol and figure out what should you pay attention to. Okay, so I can imagine that we have the functional antennas labeled as 1 and the defective antennas labeled with 0. Yes, so we have n minus m functional ones and m0 and m antennas labeled as 0. Good. So here is, and in this arrangement, the defective antennas must be separated. They cannot be all together. So you can try to imagine the situation that you have spaces between the functional antennas. So there is a space 1 before the first antenna, space 2 before the second antenna, space 3 before the third, space n minus m before the n minus m functional antenna, and there is one space after that. So altogether we have n minus m plus 1 spaces. Do you see that, guys? Now we can decide upon the pattern of for this question based on which of those spaces were selected. So I have to select m spaces for the m defective antennas where I place them here, right? So it will be simply n minus m plus 1 choose m. That's the answer to this question. Do you see how I did it? So all you have to do is just pay attention to the spaces, right? Which spaces are occupied by the defective antennas. And so you create a schema protocol, and with this protocol, you can consider every possible situation. All right, so let's now, it actually relates to a problem that has become very close to my heart ever since the semester, the in-class semester where semesters were abruptly terminated in the spring of last year. So we consider section 6, distributing identical objects among non-identical destinies. Guys, do you understand what were the multinomial coefficients about? In multinomial coefficients, we had the knights and the dragons. The dragons are the destinies. The knights are the objects to be assigned those destinies. Good? So the knights are individuals, they are different. The destinies are individuals, they are different. Good? Now we consider a situation in which we have dragons, but the knights are all the same because the knights are petty. Right? There is no difference between one knight and another. They are pawns. Do you understand? So let's consider the situation with the following problem. 5 toilet paper rolls to be divided among 6 hypochondriacs. How many partitions are possible? You understand the question? So there is no difference between one toilet paper roll and another toilet paper roll. Good? It's a Park Slope type of problem. So here is how we are going to solve it, guys. So you recognize the situation as follows. So we have 6 hypochondriacs and we designate them with the variables x1 through x6. X1 represents the number of toilet paper rolls that will be attained by one hypochondriac. X2 by hypochondriac number 2, and so on and so forth. Good? So then, have you been to the store, right? You've been to stores, I presume, right? And in those stores, you have dividers, right? You have this treadmill and you have dividers on the treadmill. So we can use those dividers to understand how to partition those identical objects. So if you have a security camera above the treadmill, you will see something like this, right? So, you know, before the first divider, those are the toilet paper rolls attained by hypochondriac number 1. Then you have between divider 1 and divider 2, there is nothing, which means hypochondriac number 2 was not lucky, right? And so on. You understand the idea, guys? So how many such dividing bars are necessary? We have 6 individuals. Let's see. If I have one dividing bar, I can partition the items of one person and another person. So one dividing bar creates 2 partitions. Yes? 2 dividing bars create 3 partitions. Do you see that? And therefore, by this analogy, you need how many dividing bars? 5, right? To divide everything by into 6 partitions, with some partitions being empty. Do you understand? So we are going to assign 2 types of objects in a sequence. Do you agree? So we have 5 toilet paper rolls, which are like zeros, and we have 5 dividing bars, which are sticks. Yes, all sticks. We have them. And you cannot distinguish one stick from another. You cannot distinguish a toilet paper roll from another. Good? So how do we address the situation? We can think very simply, right? So you understand? So this is a particular solution, right? You see the position, relative position of the sticks and the toilet paper rolls determines who gets what, right? Now, just like with the antenna problem, we can decide among those places, among the spaces where I can place a bar or a toilet paper roll, they're all together how many such spaces? There are 11 spaces, sorry, 10 spaces, not 11, 10 spaces, agree? 5 spaces will be occupied by toilet paper rolls, 5 spaces by dividing bars. You with me? Can you see that? And once you every particular sequence of bars and toilet papers identifies a particular pattern. So just like I showed over here. So the situation is now very simple. Just choose the spaces to be occupied by the bars, or equivalently choose the spaces to be occupied by the toilet paper rolls. So the answer is 10 choose 5. 10 choose 5 meaning 10 spaces, choose the 5 spaces allotted to the toilet paper rolls. Or equivalently choose 5 spaces allotted to the bars, to the dividing bars. Once you know where the bars are, you know where the toilet paper rolls. Okay, and that determines the unique situation. Make sense? So in general, this is the situation. Let's see, without more of my explanations, let's say we now have n, in general, n toilet paper rolls and m hypochondriacs, right? N toilet paper rolls and m hypochondriacs. How many partitions are possible? You understand? So, you have m hypochondriacs trying to get n toilet paper rolls. How many ways to distribute those objects among them? Okay, Andre, so that's very good, Andre. So one person already had an answer. Just let me wait one more moment and see if others see what it is. Very good, Anton. Okay, great. You okay? I already begin to see some people answering it. Good. So very simple, guys. If you understood my analogy, if not, you just ask me to re-explain it, right? If I know how many bars do I need? I need exactly m minus 1 bars. Do you agree? M minus 1 bars. And additional n spaces. So the spaces for the toilet papers plus the spaces for the bars make together n plus m minus 1 spaces. Of those spaces, I can choose n to be occupied by toilet paper rolls. Or equivalently, I can choose m minus 1 spaces to be occupied by the bars. That gives the same solution. Yes? So the answer is simply one or the other. Either n plus m minus 1 choose n, or n plus m minus 1 choose m minus 1. You see? N refers to the toilet paper rolls. M minus 1 refers to number of bars. We need 1 bar less than the number of destinies. Good? Destinies in this case, different hypochondriacs, they're individuals.
I have a question.
Yes?
You wrote 5 spaces for toilet paper rolls and 5 bars.
Yes.
Shouldn't it have been 6 spaces?
Well, because you see, we have 6 hypochondriacs, yes, but we need 1 less space, because 1 bar divides into 2. 2 bars divide into 3. You understand? So we need 6 partitions. We need 6 people, so we need 5 bars. We need 1 less. Do you see that?
Yeah, I see that, but then wouldn't m or n be 6?
No, n will be, in that previous problem, it was 5. We had 5 toilet paper rolls to be divided among 6 individuals. Obviously, some individuals will not get anything.
Oh, okay. And then the 6 is just m minus 1.
Yes, because okay. In this situation here, I illustrated the security camera footage. You can see that many of the hypochondriacs got nothing. Only 1 and 3 got something, right? The rest are just going with empty bags.
Yeah. Okay,
yes.
Thank you.
Good. You see, you all see that, guys, right? So the idea here is combinatorial problems. Once you come up with an efficient thing to count, first you have to realize what you must pay attention. What is it that you want to count? What do you encode? Yes. So then I'm not sure, guys, have you read the stories of Hans Christian Andersen? Right? It's actually very good, because today's what, when, where question will be exactly about that. right? So make sure to stay, because you will learn something about this famous fairy tale writer. Yes, that's going to be very interesting, I hope, for all of you. So Hans Christian Andersen wrote a story called The Little Match Girl. Okay, so in that story, that match girl would light a match to maybe remember how beautiful it was, remember her grandmother and what's not, right? You can read the story. It's just very touching, right? So the question is, of course, if we have M girls and N matches, M girls and N matches, how many ways to distribute the matches among those girls if it's allowed for some girls to get no matches? Understand? Some girls can be left matchless. How many possibilities? And then solve B. Now every girl, it's Hans Christian Andersen story afterwards, every girl has to have at least one match. Well, Jennifer, sure, I mean, if you cannot stay, it's not forced, right? But you are missing Hans Christian Andersen, a fact about him. That's just terrible. Oh, Grant. That's good. You see, that's called dedication, right? That's dedication. Okay. Let's continue. You understand the question, yes? Guys, again, quickly tell me, please, some girls may get 0 matches. How many ways to distribute the matches to them? That's easy, obviously, right? Anton, you're saying M plus N minus 1, choose N for part A. Everybody understands. It's the same problem we just solved before. Now, can you solve problem number B? That's a little harder, right? Now, each girl has to have one match. Okay, Andre, interesting. N minus 1, choose M minus 1. Interesting. Okay, Sarah, thank you. All right, guys, so let's look at the solution since you're waiting for it in suspense. So obviously A, we already know how to solve. Yes, it's either N plus M minus 1, choose N, or choose M minus 1. Both are correct. Now, here is what we can do for the next problem. The next problem, we are forced to have each girl must have at least one match. Good? Each girl must have at least one match. So then what do? We can arrange the matches. There are N matches, match 1, match 2, match 3, etc. And we can impose spaces in between them. There are N minus 1 spaces between them. Do you see that? Now, out of those spaces, I need partitions. You see, once I select partition, if I select a partition, that means that that it will, once I select all the partitions, that will identify which match goes to which person. Good. So I need to select exactly M minus 1 partitions. N minus 1 spaces must be selected because one partition now divides the matches to 2 girls. 2 partitions divided to 3 girls, 4 partitions to 5 girls, and so on, right? So we need M minus 1 spaces to be selected from among the N minus 1 spaces. Do you see that, guys? I no longer allowed spaces before or spaces after. So the answer is simply here, for example, right? In this situation, if I have 3 girls and 5 matches, for instance, right? If I select space number 1 and space number 2, that means that first girl got 1 match, second girl got 2 matches, and third girl got 2 matches. Yes? So that means that in general, we have n-1 choose m-1 possibilities. And that's now let's consider the general approach, right? So clearly, we already know that if we have n objects and each individual must receive at least 1 object, and there are m individuals, the situation is the number of possibilities of distributing them is n-1 choose m-1. Yes? Now we can do try to answer the question in general. What happens if I force xk to be bigger than or equal to some nk? You understand? So it's not necessarily 0. Could be even a negative number. Yes, could even be a negative number. Do you understand what I'm saying, guys? So for instance, suppose that I have some favorites. So I have let's say girl number 1 has to get at least 3 matches. Girl number 2 has to get at least 1 match, and girl number 3 has to get at least 5 matches. And I have altogether 11 matches. Right? Good. So then I have this situation, and I have x1 plus x2 plus x3 equal to 11 with the above conditions. You agree? So how do I deal with it? Well, it's very easy to reduce the situation to one that you have already solved. Okay. So for instance, I know how to solve something like x1 plus x2 plus x3 equal to some number n, where xk is bigger than or equal to 0. Do you agree? That's where we started with the hypochondriacs and toilet paper. So I can generalize that solution to every aspect. Look at this equation. How many solutions are there for x1 plus x2 plus x3 equal to 11? Given that x1 is bigger than 3. If x1 is bigger than 3, then I can say that x1 minus 3 is bigger than 0. Do you see? I subtract 3 and I call this variable y1. Do you see that? y1 is now bigger than 0. Plus x2, I can just say x2 minus 1 plus x3 minus 5. And those variables I can call y2 and y3. And to balance the equation, look at it, I subtracted 3 and 1 and 5. To balance the equation, I have to subtract, so it's 11 minus 3 minus 1 minus 5. You agree? So it's 11 minus 3 minus 1 minus 5. Yeah, which is which is 4. Yes. So we reduce the situation to another equation in which y1 plus y2 plus y3 equals to 4, but where each y is bigger than or equal to 0. You still following me, guys? You understand that if I know how many solutions exist for the equation that I wrote in red, because each solution for the red equation translates to a solution in the black equation uniquely, right? Like just if I solve this equation, I can easily convert it to a solution of the black equation. Isn't it? So is it 2? Oh, yeah, 2. Sorry, 2. Right, that's right. That's what confused you, right? It should be 2. Fine, 2. It's 11 minus 9. It's 2. Right? Good. So aside from that small thing, you're not confused, yes, guys? You understand that if I solve the red equation, a solution for the red equation immediately translates to a solution of black equation and vice versa, which means the number of solutions to the red equation matches the number of solutions to the black equation. And the red equation satisfies that yk is bigger than or equal to 0. Yeah. So that means what? That means look what we have then, right? So the fact that it's 4, it's less important. So that it's 2, it's less important to us. So we have this. We have 11 minus 1. What is it? Minus 3. Minus 3 minus 1 minus 5, right? So we have, the answer is going to be 11 minus 3 minus 4 minus 1 minus 5, sorry. Right? This is this number plus 2 or plus 3 minus 1. Choose what? Choose 2. That would solve it. Yes, this 2 guys, this 2 stands for the number of spaces that I have to select, or the bars that that divide the objects to partition into 3 parts. Good. So that's the general situation. What happens in general? You can convert it. I converted it to the situation where it's 1. You can convert it to this. You see, like, guys. So it's n plus m minus 1, and then you have, so it's n plus m. M is the number of partitions I need, minus n1, and 1 is the minimum number for person 1, and 2 is the minimum number for person 2, and onwards. Choose m minus 1. So that's how many distinct partitions are possible. You follow? Here, guys, again, if I have the situation where x1 plus x2 plus xm equal to n, and I know that xk has to be bigger than or equal to nk, all I have to do is convert to the red equation. The red equation is y1 plus y2 plus ym equal to n minus n1 minus n2 minus n sub m. Do you agree? That's because y of k is equal to xk minus nk, and I balance the equation. A solution to the, this is the situation. So it's equal to xk minus nk, which is bigger than or equal to 0. You understand what I did? I reduced the black equation to an equation that I already worked with, that I know how to solve. A solution of the red equation immediately corresponds to a solution of the black equation. A solution of the black equation immediately corresponds to a solution of the red equation, which means that the number of solutions of the red equation and of the black equation is exactly the same. You follow? Do you see that, guys? Yes? And that means that the number of integer solutions to this equation will be n minus n1 minus n2 minus n sub m plus m minus 1. Choose m minus 1. The plus m minus 1 is plus the number of bars that I have to have. If I partition into m parts, I have to have m minus 1 bars. And here I choose the spaces for the bars. Right? Well, that's a very pregnant silence. Do you understand? Or too fast?
I understand the math. I'm just trying to think through it like the other way, like like document or diagram wise in my head. That's what I'm not like
Professor.
clear with.
Well, you see, easiest to convert. Basically, it's easiest to come up. We already came up with a protocol for equations where the variables are integers bigger than 0 or equal to 0. Yes, that's the first thing we did today. So any other equation with integer solution can be converted to that first situation, because all we're counting is the number of documents, right? And if I know the solutions of the y equation, I can immediately convert them back to the solution of the x equation. You see, what do I do to convert it? Very simply, look at it. Once I know, let's say y1, to get x1, I just add to it nk, n1, sorry, right? So I add to it n1. You see, because y1 is x1 minus n1. So just add it back, you see? So you can easily convert the red equation solution to a black equation solution, and vice versa. So there must be exactly the same number of solutions to both equations. But the red one we already dealt with. We already know how to count the solutions for the red one. So I don't need to invent a new procedure. Make sense? I hope. All right. Let's move on. That's a sort of my attempt, rather silly question, of course. So my attempt to explain how such a question will be, right? So you must pay the mob at least $10,000 this week, and your bank account is empty. You then recall the prize collection of silver spoons in your family. You own 2 spoons. Your grandma has 6, and your parents have 4. If each spoon is worth $1,000 and you intend to pay your dues with spoons, A, how many ways can you do this while stealing as little as possible from your family? Okay, and B, in how many ways if stealing from family members isn't your prime concern? So I'm not going to torture you with this question. I'll show you how I set it up, okay? So it's a sort of conservation of spoons type of property, right? You can normalize so that basically you can normalize it as follows, guys, right? So if you take spoons, right? If you take spoons, you cannot take, so let's say let's say the number of spoons that you're going to give, your own spoons is 2, right? So I normalized in such a way that at the end of the transaction, the number of spoons that is going to be in the hands of your grandmother plus the number of spoons that are going to be in the hands of your parents plus the number of spoons in the hand of the mob is going to equal to 2, where the number of spoons can be negative. Negative means you take away spoons, right? So you have the default. 0 means you haven't touched. Negative means you took away. Positive means you gave. Okay, so I normalized it this way. You don't have to. I just kind of try to show you how you might have negative integers. Okay, so that means that x1 is bigger than or equal to -6. You agree? Because you cannot take more than 6 spoons from your grandmother. Now x2 cannot be less than -4 because you cannot take more than 4 spoons away from your parents. And x3 cannot be less than 10 because first they initially had 0 spoons, the mob, right? But you cannot take spoons from them, you have to give them spoons. Good. So then the number of ways to do that is then 2 plus 3 plus 6 plus 4 minus 10, and then minus 1. And the result will be 4 choose 2, which is 6.
Could you
Yes.
go over where you got those integers?
With those integers, -6, -4, and 10?
No, the ones that are in the formula.
Right. So the ones in the formula, it's just this. Once I know that x1 is bigger than -6, x2 is bigger than -4, I just convert them to y, right? So look at it. What I do, I say x1 plus 6, yes, plus x2 plus 4 plus x3 minus 10, right? Initially it was supposed to equal to 2, but now it's equal to 2 plus 6 because I added 6, I must balance the equation, I must add 6, yes? 2 plus 6 plus 4 plus, oh, minus 10, and then minus 10. Yeah? Minus 10, that's my equation, okay? And now x1 plus 6, x2 plus 4, x3 minus 10 are my variables y1, y2, and y3, and they are each bigger than or equal to 0, okay? Now, this is the number. This is my number n. Whatever it is, it's my number n. Good? So how do I solve for the number of solutions? I simply know it should be the number n the number of objects I want to divide plus 1 minus the number of partitions, right? So I had 3 partitions, so I need to add 2. So I have to add 3 minus 1, or simply plus 2, right? And then choose 2, right? Choose 2 for the 2 is the bars. Now this is my toilet papers. This is toilet papers, and plus 2 is the bars. So number of toilet papers plus the number of bars, it gives us the number of spaces on the treadmill. All right. Now choose 2 places on the treadmill for the bars, and you have the number of partitions. So that's the answer. Good. Okay, great. Now, similarly, if in general, you might consider this situation, right? If you are not, yes, good. Well, so basically, again, you don't pay attention to this formula, right? See that you can, once you, if this is the equation that you can obtain, you can set it up as a different equation altogether. But if this is the equation you obtain, and then you convert it to variables being more than or equal to 0, and you just remember, right? So you just now have another equation, variables equal to a number. Now you just think of the number they're equal to as the toilet paper, and the number of variables 3 minus 1 as the bars. 3 minus 1, in other words, I need 2 bars to partition into 3 segments, okay? That's what's important. Now, yes.
Sorry. Can I just clarify then? So then x, can you scroll up again to that problem for a second?
Yeah.
So x1 here and represent, like that x1 greater than or equal to -6 represents the fact that you can take 6 from, what was it? Sorry. Okay, so 6 from your grandma. 4 negative x2 negative greater than or equal to -4 represents you can take 4 from your parents. X3 greater than or equal to 10 represents that the mafia has to gain 10. So then, right. And 2 here represents what, the amount you own, or what exactly is that? 2,
yes, represents how much I own, right? So exactly right. 2 represents how much I own. So I set it up so that if you add up the number of spoons negative, you can have negative spoons from your family plus the positive spoons in your mob, you'll get the number of spoons you own. Okay.
Okay.
Right. You might think about, I don't want to spend too much time on the setup since you can do another setup altogether. You understand? I normalized for it to be pretty much, it's like a conservation of energy, right? At the end of the partition, you are left with 2 spoons. So you can have negative and you can have positive, but altogether it's supposed to be 2. Okay. Yes, and then this is another setup. Is that altogether how much the number of spoons? Here's another setup. That's the situation where you don't necessarily care to give away your spoons. You might keep your spoons, right, and just steal from your family, right? So in that situation, you have again you can set it up so that each of them has 0 spoons or more, and the number of all the spoons here, I make them all positive, so to speak, right? Altogether, there are 12 spoons, and they have to be distributed in such a way that the mob, this is the mob has to gain at least 10. Good. So then you have 5, choose 3, and 10. That would be 10 possibilities of distributing it. Good. So let's move on to the next lecture. Oh, great. We are finished with combinatorics, and now we are going to see how good you solve those questions. Okay, I'll give you more time to think about those ones, as it's going to be from very easy to very hard. It's going to go like this. Okay, so let's begin like this, guys. So 52 cards to be divided equally among 4 players. How many are possible outcomes? Go ahead, calculate it. You understand? You have 52 playing cards. They are each individually different. And we have 4 players. They must be divided equally. How many outcomes? Alan, careful. Choose 13, you just supplied 13 cards to 1 player. And guys, another thing is what you want to do, not only to solve this question, but do you see a protocol? All right, what do you imagine? How do you report how you gave those cards to which player? Careful, guys. Okay, good. Okay, guys. Some of you solved it. Let's do this one together now. Ready? So again, here is my protocol. So I see 4 boxes. Red box is for player 1, a blue box for the next, green for the next, and the purple or whatever that color is for the last player. Yes. Now the codes have to be placed. The cards are labeled as 1 through 52. The codes must be written in increasing order. Okay. So they are going to be. So now you can imagine the situation. Those are like trays. You have 52 knights, and they are distributed equally among 4 dragons. Do you see that? 52 different objects, different cards. Those are the knights, and there are 4 dragons. Player 1, player 2, player 3, player 4. Yes. So the answer is 52, choose 13, 13, 13, 13, or simply 52 factorial over 13 factorial to the 4th power. Do you see how that works? Why is it 52 factorial, 13 factorial to the 4th power? You can solve it other ways. Alan did it another way before, but that works very well. You can imagine arranging all the knights, all the cards, arranging them in a sequence from 1st to 2nd. Yes, and then you can see that you have those that fall into player 1 tray. They can be permuted. They can be permuted among themselves. There are 13 factorial permutations there. Independently, 13 factorial permutations for the next box. And there are 4 such boxes. Good? So independently, there are 13 factorial to the power 4 permutations. And those are the synonyms. Those codes represent the same outcome. Do you see that? So the answer is 52 factorial divided by 13 factorial to the 4th power. Now, next question, let's see if you understand it, guys. Next question is very similar. 52 cards are now divided equally into 4 piles. You see now there is no difference between, there's no destiny to the pile, just only being together. How many possibilities? Okay, great. Great, some of you see that, amazing. So now there are no categories. So additionally, we have 4 factorial repetitions because those boxes here can be moved. You see? So it's going to be the previous number divided by 4 factorial. I hope you understand it, guys. Next is this question. 52 cards are divided among 4 players. Such that each player may receive any number of cards from 0 to 52. How many possibilities? Okay, a lot of you got it right, I see. Good. Good. All right, are you ready? All right. We can, of course, be slower if you go to office hours, guys. So here is the situation. So we have cards 1 through 52. So I have my document will contain 52 boxes, and each box is assigned the number 1 through 4. So that means card 1 is assigned, let's say, if 1 is placed here, that means card 1 is assigned to player 1. You see? So by the multiplication principle, we have 4 to the power of 52 possibilities. You get it? Because now, I mean, the way I decide to allot the partition is that each card, I just decide individually for this particular card which player it will be going to, because I don't have to have equal piles, right? So it will be 4 to the power of 52. Next question is 52 cards divided into 4 piles. The piles are not necessarily of equal size. How many partitions are possible? This one is difficult. Okay, this one is a bit difficult. Into 4 piles, the piles are not necessarily of equal size. How many partitions are possible? I kind of don't want to, you would not maybe able to come up with an answer on the spot, and I would like you to think about it, right? So maybe what we'll do, we will solve a different set of problems for a moment. Let's see if we can do that. And at this point, you consider before the next class how to solve the situation. Good. Let's see if we do another set of problems. You understand what's happening here, guys? So we are changing situations, right? We are we consider now that we consider different cards divided among different people, and now we are considering you know, that different cards are divided into piles, but there is no no assignment to which person it goes. Yes, the people can afterwards take any pile or not take at all, right? You see, so there is no, it's not clear who is assigned what. Okay, and yes, Sarah, you are exactly right. In this, you see, in the previous case, it was a bit simple because I could just specify which card is taken by which person. But here, it's not distributed to people. You just have piles. Right, so that's a bit difficult. See if you can come up with an answer. So Jeffrey says something. No. You see, Jeffrey, you divide by 4 factorial. What makes you divide by 4 factorial? You see, when you divide, you are saying that each particular situation is repeated 4 factorial times. That's why you divide. You understand, guys? When do you divide? It's this situation. Look at it. Imagine that each person has 2 phone numbers. Okay, each person has 2 phone numbers. If there are 12 numbers, how many people? How many people do we have, guys? It's a simple question, right? Each person has 2 numbers. How many people do we have? We have 12 numbers, 12 phone numbers. How many people do we have? Exactly. Do you all see that it's 6? Yes. What do? You take numbers divided by 2, which gives you 12 divided by 2, which gives you 6. Do you understand? What are those phone numbers? Those are codes. So those are synonyms, right? Each phone number is a synonym for a person. So if I have 2 phone numbers, right? One phone number is me and the other phone number represents me. Those are both words that represent me. Yes? So that's why I divide. You understand? If I know the number of words, I just need to divide by the number of synonyms and I'll get the number of people. Right? If I have the number of phones, divide by you know, by how many repetitions per person, and you get the number of people. James, you were saying?
So I understand why you divide by 4 because you're getting the piles, the amount.
I didn't
right?
say. I mean, I don't agree with the person saying dividing by 4. I would say the person is wrong.
Okay.
Right.
But,
so I'm saying, that's why I went to do this explanation, right? So I divide by 2 in this situation because each person has exactly 2 phone numbers. Okay. Now, if that situation were not true, let's say some people have 1 phone number and others have 5 phone numbers. You understand? Then there is no reason to divide.
Oh, okay.
You see that, guys? It's not as simple, right? The situation is that each particular individual has exactly k names. Then you divide by k. If you know all the names, you divide by k and you get the number of individuals. Okay. If every single one of you had 5 names, then if I could know all your names, I need to divide them by 5 and I'll get the number of people. But if some of you have 5 names and some of you have 3 names and some of you have 1 name, it's much more messy. I cannot simply do that.
So like, how would you like, because it's different amounts in a pile, right? Like that's kind of, I don't know how to, because that means that you have to, I would say, not divide. I can't say divide because that's not gonna help, but you have to give off like a certain, like it's like dividing X. You don't know what's the number is to divide by because of the amount of the pile. So
So
how would you?
it's a hard question, or perhaps you solve it differently, guys. So when you get your hypothesis, my suggestion, see if it works for a much smaller number of cards. So start maybe with 5 or 6 cards and see if you can figure out the answer for 5 or 6 cards. So if whatever you write, whatever formulas you write, does it work for 5 or 6 cards? Okay. Does it work for 7 cards? You understand? You can try to think like this. Start with basically divide into 4 piles, divide maybe 6 cards or 5 cards, and see. So some of you were writing me some solutions. Does your formula work for fewer cards? And the next class, I don't want to show you today. I will show you how I figured the solution to it, what sort of solution I came up with. Okay. But I don't want to do it right now since it will take you, I think it took me also some time to figure my solution, so it might take you that amount of time to do so. So let's do this. Since we already we already figured out something about combinatorics, let's see about review problems. Okay, we have some selection of problems here that we can do, which might be easier for the moment. Okay, so here is problem number 1. Fred is planning to go to dinner each night for this week, Monday to Friday, with each dinner being in one of 10 restaurants. Yes, you should tell Fred that it's impossible to do that anymore, and maybe never will be. How many possibilities are there if Fred will not go to the same restaurant twice in a row, or more than that, or so? What am I saying? Not go to the same restaurant twice in a row. That is, he can go to the same restaurant several times, but not consecutively. Okay. The more means, let's say, he cannot go. It cannot go to the restaurant within 3 days or whatnot, right? So we begin this problem by saying he cannot go to the restaurant on the next day. So if you go to restaurant number 1, the next day cannot be restaurant number 1. Can you tell me how many possibilities are there? Well, Andres says 10 times 9 times 8 times 7 times 6. Sarah is saying something else. Okay. Think about it for a few moments, and then we will solve it together. Okay, Alan is also saying something different, so slightly different from all 3 that responded are saying different things. Interesting. Okay, Jennifer, interesting. All right, so let's solve it together, I guess. Okay, Alan, great, amazing. Okay, so let's see what the solution will be. So we have this protocol. So this is day 1, day 2, day 3, day 4 onwards. You agree? We have those different days. So how many possibilities, how many choices are there for day 1? Clearly there are 10 choices. Do you agree? Next day, the choice that was made for the first day is deleted. I cannot use that choice, yes? So one of the 10 numbers is not available to me. So that means this will be 9. Do you agree? Now the next day, what happens on the third day? On the third day, I don't have access to the second position code, but I do have access to the first restaurant, right? So again, I am only locking 1 day. So it's another 9. Do you all see that? So it's 9, and then the same thing for all the remaining ones. Yes, if you have to wait at least 3 days, then you know the code starts being recycled after 3 days. Good. Here, I mean, you understand, guys, how it's 10 times 9 times 9 times 9, right? It's because I only cannot access to this code. So at position 3, I cannot access to the code written for position 2, but I can access the number that was in position 1. Yes. So I'm always locking one restaurant where I cannot go. I hope it's clear. All right, so now 20 people in a chess club divide in pairs and start playing. How many playing arrangements are possible if it matters which player is assigned to play the white pieces? Okay, interesting. Be careful, guys, right? It matters who plays against whom and which person plays which pieces. Yes? If they divide into pairs, think about it this way. If divide into pairs, how many pairs do we have? Right? So that is something we need to know. All right, so some people say 20 factorial divided by 2 factorial, 2 factorial. Some say 20 factorial divided by 10 factorial and multiplied by 2. All right, let's see. I wait a little bit longer and then we solve it together. 2 more minutes. You have to create codes, guys. You have to be a bureaucrat, right? So you are reporting on this chess tournament, and you're reporting what? Who played against whom, and who was playing the white pieces, right? Because if you reported who plays the white pieces, obviously the remaining ones are playing the black pieces. You understand? So you have to imagine a protocol that once I read it, I know exactly which people played against which other people and what was the color of their pieces. That's the information we need for this problem. Okay. Let's see how many we have here. Guys, Kafka Protocol. right? And if you don't know why it's called Kafka Protocol or why I call it, you read Kafka the Castle. All right, so 20 factorial. All right. So far, not a single person answered it correctly. It's fine. I'm pushing you. It's very pressured, of course, right? I'm just trying to push you too fast. All right. Let me show you how I would think of it. Okay. You have to understand, guys. I right away imagine a report. Okay, because you can make millions of mistakes if you do not imagine the report. Okay. So here is my report. So here is the way. Okay, James, interesting. So first report is white. Who plays white? So in white, I have 10 boxes. Do you agree? Those that are playing white cannot be playing against each other. Do you agree? Because white plays against black. So then we have 1. Here we have 2, 3, blah, 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 all the way to 10, right? So I first need to report who plays white. By the way, maybe the way I drew the boxes is not quite right. I prefer to make them like this, okay? And where the code is going to be written in sequential order. You understand? So I imagine that the individuals are assigned a number. So they have a number from 1 through individual holding the number 20. Yes? And once I select the particular 10 individuals that are holding, are going to play white, they will be listed from smallest number, from smallest rank to highest rank. Do you understand? So how many possibilities are there to select people to play the white? Huh? How many ways to select people to play the white? 20 people together. How many ways to select people playing white? Not 20 factorial, guys. No, no, no. 20 choose 10. Yes, 20 choose 10. So this number is 20 choose 10, or 20 factorial divided by 10 factorial, 10 factorial. Yes? I did not finish. This document so far specifies only how to select the people playing the white pieces. Good. Next, I will need, so now they are ranked in order. You understand? They are placed here, you know, I'm sorting them from smallest to largest. Next, which individual of the remaining 10 will be positioned to play against the first person with white, the first person that is white. Then the second individual among not the ones that are to play black, where is he going to be positioned to play the next white? Okay, so then here the boxes are divided, so it's like this: 1, 2, 3, 10. Yes, and then how many ways to position the individuals here? Here we have remaining 10 individuals. So first individual, right? It's going to be 10 times next individual 9 times next individual 8. So now it is 10 factorial. Do you see that? By the way, maybe somebody did answer it right. I don't remember if I saw it. Yes. So the answer is yes. Sorry, I did. So Sarah, you are right. My apologies if I said something else. Yeah, I didn't see it, I guess. So the answer is 20 factorial choose 10 divided by 10 factorial. Yeah, so it's 20 choose 10, my apologies, times 10 factorial, which is 20 factorial divided by 10 factorial. It's just by default, I say no. You should know that, right? As soon as I hear anything, I right away say it's incorrect, and only then I consider maybe maybe I'm right. It's like in the 15th century, you are guilty and you have to prove that you are not. Okay? So good. Congratulations, Sarah, and anybody else that I incorrectly accused of witchcraft. Good. So this ends this particular problem. And great, Andre, my apology to you as well, right? If you want me, I will write my apologies here. By the way, I cannot write I apologize because I cannot even spell it. So fill in the blank. Good. But you are great, great. So if you wrote 20 factorial divided by 10 factorial, you were absolutely right. And my apologies for claiming that you are not. Good? All right, guys. So we have only 4 minutes, and so that maybe all of you may enjoy Hans Christian Andersen. I will pause, and for the next 4 minutes and a little bit more, we will talk about that what, when, where problem. Good? Get ready.